We now know how to differentiate powers of x, or any number of powers of x's. So for example, suppose we had a function like 6x to the 7. We know that to differentiate that, to find dy dx, you take the 6, stick it in a bracket and worry about it later, differentiate the x to the 7, giving you 7 lots of x to the 6, then multiply those two bits together, in this case giving us 42 x to the 6's. Okay, well that's fine. We can now differentiate things of this kind. We can differentiate anything of the nature kx to the n. The general rule then being that we will get a dy dx, we'll get a gradient function of k times n times x to the n minus 1. What if we actually want to differentiate a full polynomial? In other words, what do I mean by a polynomial? I mean various different powers of x's all strung together. So maybe we've got 3x squared subtract 5x's plus 2. How could we differentiate that? Well, it turns out that the rule is as simple as it could possibly be. You just go through this thing, differentiating each piece in turn. By pieces I mean the bits which are separated by the plus and minuses. So differentiating 3x squared, we will now probably be able to do this in our head. There's no always every need to write this formal process. It'll be 2 times 3 times x. It'll be 6x's. Differentiate the next piece. Oh, remember, if you have a number times x, it just differentiates to that number. So if I've got negative 5x's, it will just differentiate to negative 5. Oh, and remember as well, if you just have a number, y equals 2, that differentiates to 0. So we don't need to write down anything at all there. So if we want to differentiate this expression, we do it in the way we've just seen. Differentiate each piece term by term and string them together. So dy dx is 6x subtract 5. Let's just work through an example with more pieces, just to make sure that idea is clear. Suppose we had 2x to the 5 subtract x to the 4 plus 4x squared subtract 3x plus 1. Well, dy dx in this case then would be 10 x to the 4's subtract 4 x cubed plus 8 x's subtract 3, and I don't have to write anything where the number is, that just vanishes. All of this is a special case of the fact that if you are making y out of, well, we could say just two pieces, suppose it is made of some function plus another function, so these two, the x's are indicating that both f and g are some functions of x, then what we'll get when we work out dy dx is just what we get when we differentiate the first function added to what we get when we differentiate the second function. This is a piece of notation we haven't seen very much in these videos so far. D by dx of a thing just means differentiate this thing. So in that respect you can see that we're just applying this again and again when we've got lots of pieces strung together. It doesn't have to just be two. In this case, for example, we've got 1, 2, 3, 4, 5 bits strung together. Just go through and differentiate each piece on its own. So now we can differentiate fairly sophisticated polynomials. Let's just look at a question of the kind that you may be asked. Find the gradient of the function y equals x to the 4 subtract x squared plus 3 at the point where x is 2. Well, what do we mean by the gradient of this function? We mean what is dy dx. So we start off by working out dy dx. So using our new rule, differentiate the x to the 4 bit, 4x cubed. Differentiate the negative x squared, we'll be subtracting 2x. Differentiate the 3, oh, it will vanish. We don't need to worry about that bit. So that is the gradient function at any point on the curve, but we are specifically interested at the point where x is 2. Well, if x is 2, that means that dy dx is 4 lots of 2 cubed, subtract 2 lots of 2, which is 4 lots of 8. Subtract 2 lots of 2 being 4, and 4 8s are 32, subtract 4 means the answer would be 28. So the gradient of this curve at that point is 28.